Okay, so this time we will solve for the tutorial on the topic of pressure and fluid static, and these problems basically focus more on the manometer and also the pressure depth. Okay, so for the first question here, this is the theoretical question. Define Pascal law and describe an application that utilize the law with the aid of an illustration. So this question you can refer to the textbook. Also for the second question, state the meaning of absolute pressure, gauge pressure, and also vacuum pressure. You can refer also on the textbook. Right, so for the third question here, figure 1 shows a cylindrical pressurized tank that contains of air, oil, water, and mercury. The specific gravity Sg of oil, water, and mercury is 0.96, 1.00, and 13.6 respectively. Calculate the absolute pressure of the air in tank. So you highlight the important things here. Okay, so the first one is it mentioned about the specific gravity. Okay, this one is for oil, this one is for water, and this one is for mercury. Jot down your specific gravity here. Sg for the oil equal to 0.96, Sg for the water equal to 1.00, Sg for the mercury equal to 13.6. Calculate the absolute pressure P atm of the air in tank. So this is the air, means that there are a gap between the oil and also water. Alright, so that's all the question. Okay, so basically the pressure at the air we can assume to be same at each point of the of that gap. So here the pressure is constant, because the pressure variation between the top layer of the air and also bottom layer of the air is very small, and we can neglect the difference. Right, so here we can just assume that the pressure is there. We name that point as A. Okay, so the second one here is B. Okay, which is the horizontal line here. Okay, is B also, because this is the same fluid, mercury. So this is point B also, and then this is point C, when it exposed to the atmosphere. So we can state that the pressure at point C basically equal to pressure at the atmosphere. Okay, so in order to answer this question, we can start from point C or point A. So in this case, I will start at point A first. Okay, so we'll use the black one. PA plus, okay, because we are going downside here to point B, so we need to add the pressure. Okay, when we add the pressure, the value should be in terms of rho g hash. So the difference of H here is from A to B, hash AB, and then from point B to point C, it go upward, so we need to minus rho g hash from point B to point C. This one is equal to atmospheric pressure. Okay, so you rearrange because we want the atmospheric the atmospheric pressure is already given as 101.325. We want to get the pressure at point A, so you rearrange the equation. PA equal to P atm minus rho g hash AB plus rho g hash BC. Okay, so for the rho, I forgot to put what is the density for each of this term. Okay, so from A to B, that is density of water, so you put here rho of W. From point B to point C, that is the density of mercury. Okay, so here you can put all of the value. So PATM basically is equal to 101.325 kPa minus, so this is rho of water, and also this is for Hg. Okay, so rho of the water basically is not given directly, but it gives you the value of specific gravity of the water there. Okay, so you can use Sg water. Okay, and then you multiply with 1000, so that is your density of the water. Alright, and then multiply with G 9.81. Okay, so your HAB from point A to point B basically is equal to 0.1 meter, and then you add with, okay, I put down here, plus rho Hg equal to Sg of the mercury multiply with 1000 multiply with G multiply with the distance or depth between point B to point C, which is equal to, so B to C basically equal to 0.1 plus 0.1 or 0. Here is 0.3. This is the total length. Okay, you need to minus with 0.1 here, 0.3 minus 0.1, so this is the distance of HAB. When we deal with the units now, okay, because the first term here, if you see, the unit is in kilopascal, but this term, okay, is a SI unit standard that we use, and it will produce the unit of Pascal only. So in order for us to convert into the same unit kilopascal, we need to divide by 1000 here, and also the last term here also divide by 1000, so that all of these three terms will produce the consistent unit of kilopascal. Okay, so don't make mistake, and then we will put the numbers. Okay, 101.325 kPa. This one is Sg for the water 1. Right, so this is 1000. You can cancel out with this value 9.81, 0.1, and then you can put plus here, same here, 1000. You can cancel out with each other. So the Sg for the mercury is 13.6. This one is 9.81, and then the difference of distance here, 0.3 minus 0.2 is minus 0.1 is equal to 0.2. Okay, so the unit consistent in kPa, and also this one is kPa. So the answer that you will get is 1 to 7.03. Okay, so this is the question number 2. Question number 4 here, figure 2 above shows a 6 meter deep tank contains 4 meter of water. Sg for the water is equal to 1, and 2 meter of oil. Okay, you have 4 meter water, 2 meter oil. Sg for the oil is 0.88. Estimate the gauge pressure at the bottom of the tank, point A. Okay, this question asks for pressure at point A, but you need to use the gauge pressure. So because we deal with gauge pressure, means that your atmospheric pressure here, PATM, equal to 0 kPa. Okay, because this is a gauge pressure. Alright, so in order to solve this problem, we can start from point A, and then we look point B here, and then we have atmospheric pressure at the top of that oil. Okay, so here if we start from point A, okay, PA, this is question number 4. When we go upside, we need to put minus sign, minus rho of the water, multiply with G, multiply with the distance or the depth between point A to B, HAB. Okay, and then you go upside more, minus again, let's say the atmospheric level is point C, rho of the oil, multiply with G, multiply with HBC. This one is equal to PATM. We know that atmospheric pressure is 0 because we refer to the gauge pressure. Okay, so your P at point A equal to rho WG HAB plus rho oil G HBC, okay, which is equal to, so the density of the water given here by representing through SG, specific gravity. SG for water, you need to multiply with 1000 kg per meter cube, then multiply with gravitational acceleration here, then multiply with the distance from point A to point B, which is 4 meter. Okay, and then you need to plus with SG for the oil, multiply with 1000 kg, 1000 kg per meter cube, multiply with 9.81, meter per second square, multiply with the distance between point B to point C, okay, which is 2 meter. Again, your unit must be consistent. Okay, so the top, the first term, the unit is in Pascal. The second term, the unit also in Pascal. Okay, so it depends on you which whether you want to maintain the unit of Pascal or you want to convert into kilopascal. So if you want to convert into kilopascal, you divide by 1000, so you get the value of the unit of kilopascal here. So now your value becomes, this is 1000 can be cancelled out, 1000 can be cancelled out. Sg for the water is equal to 1, then 9.81, this one is 4, plus Sg for the oil is 0.88, then you multiply with 9.81, multiply with 2, so you get the answer in kilopascal. So value is okay, calculate 56.51. Okay. Okay, question number 5 here. A manometer is used to measure the gas pressure in a tank. The manometer fluid has a specific gravity of 0.85 and the manometer column height is 55 cm as shown in figure 3 below. So this is your figure 3. if the local atmospheric pressure is 96 kilopascal, determine the absolute pressure within the tank. Okay, so this tank basically contain a gas. Okay, so it already mentioned here, gas means that if the gas every point here your pressure is, we consider as same until it reach at the boundary between this gas and also the fluid. Okay, so let's say this as point A. Okay, alright. Then after the gas at the layer, we have another fluid which is with Sg of 0.85 here, and then the manometer column height between point A and also the atmospheric level, or we just put here point B. Okay, is 55 centimeter as shown in figure. Right. If the local atmospheric pressure is 96 kPa, means that your ATM, okay, PB equal to 96 kPa. This is equal to the atmospheric pressure lah. So here it's not the standard atmospheric pressure. It use the value of 96. So it asks for the absolute pressure within the tank. So it asks the value at point A. Okay, so in order to answer this question, we start from point A. Okay, so this is question number 5. PA, sorry, I use the black color. Okay, PA, and then it goes to point B. Okay, because there are no other fluid between point A to point B, so you can just minus, okay, because it goes upside, rho of the fluid multiply with G, multiply with the distance between point A to point B. Okay, this is equal to pressure at point B, or atmospheric pressure. So in this case we want the pressure at point A. So PA equal to PB plus rho FG HAB, so that we know that pressure at point B is already given, which is equivalent to atmospheric pressure 96 kPa. Then you plus with the density of that fluid, basically represented by specific gravity of 0.85 SGF. Then you need to multiply with density of water, and then multiply with G, 9.81 meter per second square, multiply with the distance between point A to point B. So point A, there is 55 centimeter, so you can convert into meter. 55 convert into meter. Okay, it becomes 55 times 0, 10 minus 2 meter. Okay, this is your HAB, and then you divide by 1000 to convert the unit from Pascal into kilopascal. So here 1000 can be cancelled out with each other, becomes 96 plus, okay, Sg of the fluid is which one, 0.85, then 9.81, then 55, 0.55. So you get the answer as 100.59 kilopascal. Okay. Okay, question number 6 here. The gauge pressure of the air in the tank shown in figure 4 above is measured to be 80 kilopascal. So figure 4 so figure 4 is here. Okay, 80 kilopascal in the gauge. Right, determine the differential height hash of the mercury column. Okay, mercury column hash. Which hash we refer to? This one, this hash. Right, so we refer to this diagram or figure. Okay, so let's say we start from a point A here. Okay, that is exposed to the environment A, and another fluid that is contact with oil is mercury here. So this is your point B, and then after mercury will contact with point C here. Okay, that is contact with water, and then this water basically contact with air, so that the pressure of the air basically equal to 80 kilopascal. So this is the gauge pressure. Right, means that PA equal to 0 kPa because we refer to gauge pressure. Okay, so here we can start from point D or point A, and the pressure of the air inside the tank basically equal to pressure at point D. Okay, let's say we start from point A. Okay, so this is question number 6. Okay, sorry, I used the black color again. So question number 6, PA, right? Then we move downward from point A to point B plus rho of the oil multiply with G multiply with hash AB from point B to point C. Okay, we need to plus again because it goes downward. So this is the density of the mercury multiply with G multiply with hash. So hash BC basically equal to our intended in this question. Okay, so we want to find the hash value, so I just let it as hash. And then from point C to point D is water, so we need to minus because it goes upward. Rho of the water multiply with G multiply with hash CD. Then we already reached to point D. Okay, so this is the pressure at point D, which is equivalent to 80 kilopascal. Okay, so here your PA basically is 0 because this is gauge pressure, while PD is equal to 80 kPa. Okay, so here your hash. Okay, we want to get the hash value, so let's say we rearrange this equation. Rho hg hash at the mercury side we put on the left hand side. Rho hg g hash, right, equal to minus rho oil g hash AB plus rho W G hash CD plus 80 kPa. Okay, so we have basically 4 terms left because we already cancel out the pressure at point A. Now you need to make hash as the main idea here. So hash equal to this one is equal to minus rho oil G hash AB plus rho W G hash CD plus 80 kPa, right, divide by rho hg multiply with g. Okay, so this is a quite a length equation, but the main thing that you need to remember here is the unit. Okay, so make sure your unit is consistent. This is kPa. Okay, so our term, the three terms, rho of the oil, rho of the W, and also rho for the mercury, basically all of these three terms use the unit of Pascal only, because we did not divide by 1000. So to make it consistent, we need to divide by 1000 for each of these terms. So this one I divide by 1000, 1000, and also this one also 1000. Then you can expand it, put the value for the density equal to density for the oil basically equal to Sg 0.72 negative 0.72, and then you put your value of 1000 because this is the Sg. Okay, and then you multiply with G 9.81. Okay, then multiply with the distance from point A to point B. Okay, from point A to point B is 95 centimeter. So put here 95 times 10 minus 2, okay, meter, and then divide by 1000. So this is the first term here. Okay, put the density of your water. Density of the water basically equal to 1000. Okay, and then multiply with G 9.81, and also the distance from point C to point D, which is equal to 40 centimeter, or you convert into meter, 40 times 10 minus 2, right? So we add, or we will divide by 1000 first, then 80 kilopascal, then you divide by rho hg, which is equal to Sg for the mercury 13.6 times 1000. Okay, and then okay, sorry, this we left one terms here, which is your hash. Okay, sorry, okay, we already put it hash on the other side, so this is your hash that we want to find. Okay, divide by 1000. So you simplify the equation, 1000, 1000, 1000. Okay, so you can simplify this. Okay, so I forgot to put here 9.81, right? So because we have G there, then we calculate negative 0.72 times 9.81 times 95 exponent minus 2. This is equal to negative 6.7100 plus 3.924 plus 80 divided by 13.6, 133.42. So you got the answer as 0.5787 meter, which is equivalent to 57.87 centimeter. Okay, that's about question number 6.